Okay, this is a question related to the alkanes topic, one of the early parts of organic chemistry. There are a couple of sections to it. I'm going to recommend that you pause on each section and try the question, then move through and review it once you've tried to write down each of your answers. So pause the video here. When you're ready, move on and pause. Moving on to part D, pause. And moving on to parts E and F, pause. Okay, so let's go back to the beginning of the question. You're being asked for the general formula, which is a straightforward factual recall question. You need to remember that an alkane is CnH2n plus 2. The second question takes a little bit more thought. It's a much more uncommon question. But the way that you can think about this, if you want the MR of any alkane, is we know we have N carbons. Now, if I look at this particular carbon here, it has two H's attached to it. Ignore the one on the end just for now, because there are lots of carbons that have got that exact pattern, a carbon with two H's. In fact, I've got N of them. So my total MR for all of these components is 14 multiplied by N, or 14N. But what an alkane will always have is an H on each end of the carbon chain. So for that reason, it becomes 14N plus 2. On to the next question, we want to know why nonane has a higher boiling point than 2,4-dimethyl heptane, and they both have the same molecular formula, C9H20. So it's not about their size per se. But if I take a look at what we need to know, first of all, we're relating it to stronger van der Waals forces, that if the boiling point is higher in an alkane, it has to be the van der Waals forces that are stronger, because they are the only intermolecular forces that exist. And why is that? Well, it's because nonane has a greater surface area. The minute that you add branching, you drop the surface area. And so there's less opportunity for the intermolecular forces to act between the molecules. Moving on to the equation for the complete combustion of nonane, I've already said that it's C9H20, and you can work that out from the diagram earlier on. And we know in combustion that we react with O2. The fact that it's complete combustion means we know we're making CO2 and H2O. Whenever I'm balancing the combustion of a hydrocarbon, I will always follow the rule of Cho. I will balance the carbons, followed by the hydrogens, followed by the oxygens. So C9 means 9 CO2. 20 H's means 10 H2O. And then I've simply got to work out how many O2s I need. So I've got 28 oxygens on the right hand side, so I need 14 O2s so that I can balance the equation. On to the next question, and we're talking here about pollutants, and specifically about nitrogen monoxide, which is one of the causes of acid rain. Now, it's a 2-mark question, or a 2-mark answer I should say. How is nitrogen monoxide formed? Well, let's keep it really simple to begin. What must nitrogen react with to form nitrogen monoxide? It reacts with oxygen from the air. But then we hit a little bit of a sticking point, because 78% of the air around us is nitrogen, and it doesn't ignite. We just don't see it. But in very specific circumstances, it will. In a car engine, it will. In jet engines, it will. When lightning strikes, it will. And what is it that makes a difference there? It's the fact that we have very high temperatures. Okay, finally, moving on to part E and F. E is very much a factual recall question. You've got a table that you will need to remember about what type of cracking gives what type of products. And for this one, we would need to say thermal cracking. When it comes to the repeating unit of polypropene, which is actually creeping into the alkenes topic, I'm going to start off by drawing propene itself, the monomer. Drawing it this way often poses difficulties. It often leads to the wrong answer, and you will very often see the repeating unit as the double bond gone and the three carbons in a row with the bond going to the repeating unit coming from the first and third carbons. But that can't be the case. That would mean hydrogens would have to jump from one carbon to another. So let's redraw that monomer in a different way. And let's draw it in the standard format that I would always recommend. Because the minute you do that, you can visualize where the double bond will break, the bonds will move out to the other side of the carbon, and they will burst out so that they can meet the next monomer in the repeating unit. And this is the repeating unit that we were looking for.